Dear students, today we are going to discuss the AASHTO rigid pavement design method. The design equation which is used in this method is quite complex. You can see different variables are involved, and here in this equation this D is representing the plain cement concrete thickness, or simply you can say the thickness of the concrete slab. So in this equation, if you just look at the different variables, W18, W sub 18, that is the design traffic, that is the accumulated equivalent single axle loads, Z sub R, that is the standard normal deviate, S sub naught, that is the combined standard error of traffic and performance prediction, D is the thickness of pavement slab in inches, and delta P SI, that is difference between initial and terminal serviceability indices, and P sub T, that is the terminal serviceability value. S sub C dash, that is the modulus of rupture for Portland cement concrete in PSI. J is the load transfer coefficient. C sub D, that is the drainage coefficient, and E sub C, that is the modulus of elasticity for Portland cement concrete in PSI, pound per square inch, and small k is the modulus of subgrade reaction, that is pound per cubic inch. Well, keep this thing in the mind that the k that is being used over here, that is the most corrected value of the modulus of subgrade reaction. Certain corrections are to be applied on the modulus of subgrade reaction, and ultimately will be having the corrected modulus of subgrade reaction, and that will be used in the equation. Just to facilitate the engineers dealing with the pavements, nomograph has been developed to determine the thickness of the concrete slab. So the different variables that I have already highlighted on the previous slide, we must be knowing the values, and by using those values ultimately we'll be able to determine the depth of the concrete slab. Now here you can see effective modulus of subgrade reaction, that is the corrected value, the most corrected value. Let's say that is this one. So starting from here, and then look at these curves, set of curves for the concrete elastic modulus. So for different concrete elastic modulus E sub C, we are having these. Let's say we are having the concrete elastic modulus equal to this. So we will draw this line in this fashion, and after reaching here we will move horizontally like this, and we will reach over here. Then look at this one. This is the modulus of rupture of concrete. So let's say the modulus of rupture of the concrete's value is this one. So from this point we will draw this line in this way, and we will reach over here. This is the turning line, TL, that is the turning line, this one we have reached here. Then look at this one. This one is meant for load transfer coefficient. Let's say the load transfer coefficient value is this one. So from this point we will draw this line in this way, and we will reach this turning line at this particular point. After reaching here, look at this one. This is the drainage coefficient. Let's say the drainage coefficient value is this one. So starting from here and considering the value of the drainage coefficient, just draw this line and reach here. This is the again the line which is considered as the match line, And if you just look at that, it is nearly equal to 74 value. Now the next part of the nomograph is present on the next slide. Okay, you can see this is same match line which was present on the previous slide. So you can say it is 74. So starting from here, and look at this one. This is the delta PSI, that means design serviceability loss. Let's say the design serviceability loss value is this one. So just draw this line and reach here. Now after reaching here, just look at this one and look at this bar. This is representing the reliability. Let's say the reliability is this one. The next thing that you can see over here, that is the overall standard deviation, and let's say the overall standard deviation value is this one. So just draw this line and reach here, this turning line TL. And if you just look at this one, this bar is meant for the accumulated equivalent single axle load. Let's say the equivalent standard axle load, that is this much. So just draw this line from this point to onward and reach here. So we have reached here. We have already reached here. Now from this point, just draw a vertical line, and from this point draw a horizontal line. So in this way you will be having the point of intersection, and you can see that these are the curves for the slab thickness. So in this way we can determine the thickness of the concrete slab. So simply you can see that by using the different variables and using the nomograph, ultimately you will be in a position to determine the design slab thickness. Well, I would like to say something about the reliability which is there on this particular bar. The AASHTO guide incorporates in the design a reliability factor R, capital R in percent, to account for uncertainties in traffic prediction and pavement performance. Capital R in percent indicates the probability that the pavement designed will have a performance level higher than the terminal serviceability level at the end of the design period. So it is some sort of, you can say, the factor of safety that is being considered in the analysis. Okay. On this particular slide, you can see again the design inputs that we have used. But on this particular slide, you can see W sub 18, that is the design traffic, 18 equivalent single axle loads, or simply you can say accumulated equivalent single axle loads. Z sub R, the standard normal deviate. S sub naught, combined standard error of traffic and performance prediction. Delta PSI, that is the difference between initial and terminal serviceability indices. P sub T, the terminal serviceability index. Well, all these inputs, these all consistent with flexible pavement. That means we also considered these inputs in the case of flexible pavement. Well, on this particular slide, you would find additional design inputs. And the additional design inputs in the case of rigid pavements: S sub C dash, modulus of rupture for concrete. J, joint load transfer coefficient. C sub D, drainage coefficient. And E sub C, modulus of elasticity for concrete. K is the modulus of subgrade reaction, but this is the corrected value of the modulus of subgrade reaction. Additional inputs reflect differences in materials and structural behavior. On this particular slide, you can see the joint load transfer coefficient J, and you can see here JCP and JRCP with load transfer devices, JCP or JRCP without load transfer devices, and CRCP. So keep this thing in the mind that JCP stands for jointed concrete pavement, JRCP stands for jointed reinforced concrete pavement, and CRCP stands for continuous reinforced concrete pavement. So you can see that we are having the smallest joint load transfer coefficient value in the case of CRCP, that is 2.9. But if you just compare these two cases, JCP or JRCP and JCP and JRCP with load transfer devices and without load transfer devices. So you can see that when the load transfer devices are being used at the joint, so the joint load transfer coefficient value will be smaller. So keep this thing in the mind that joint load transfer coefficient is small when there is effective load transfer at the joint. Keeping this thing in the mind that the joint is the weakest part of the rigid pavement. Now on this particular slide, you can see the types of rigid pavements: jointed plain concrete pavement, JPCP or JCP, so does not use any reinforcing steel. Then comes jointed reinforced concrete pavement, JRCP, reinforcing steel placed at mid-height and discontinued at the joints. Then comes continuous reinforced concrete pavement, CRCP. This method is very costly. And then pre-stressed concrete pavement, PCP, comprises new and innovative construction methods. Precast pavement components are fabricated and installed on a prepared foundation, that is existing pavement or regraded foundation. So in this particular slide, you can see the jointed plain concrete pavement. This is the top view and this is the side view. You can see the transverse joints and the longitudinal joint, and in the side view you can see the dowel bars which are to be provided at the joint. This particular slide is showing the jointed reinforced concrete pavement, JRCP, and you can see the longitudinal joint, the transverse joint, and at the joint we are having the dowel bars. But as this is the jointed reinforced concrete pavement, so we are having the reinforcement in the panels of the concrete. This slide is showing the continuously reinforced concrete pavement. So you can see the steel is continuous even at the joints. That is why it is called as the continuous reinforced concrete pavement, CRCP. And here you can see the different types of load transfer devices. So such type of load transfer devices can be placed at the joint so that you are having the effective load transfer at the joint. So load transfer coefficient, additional benefits of tied shoulder. If a shoulder is provided on the side of the rigid pavement and it is tied with the road, so you would find because of that there will be decrease in the value of the joint load transfer coefficient. Look at that. Plain, jointed and jointed reinforced. Here yes means the load transfer device has been provided. No means no load transfer devices. So this is the asphalt shoulder, and this is the tied PCC. So just look at that. When we have provided the tied shoulder, so you can see that there will be further decrease in the value of the joint load transfer coefficient. For example, here 3.8 to 4.4, here 3.6 to 4.2, here 3.2, here 2.5 to 3.1. While in the case of continuous reinforced concrete pavement, we don't need to provide the joint load load transfer devices. So that's why here it is written no applicable, not applicable. Well, in this particular slide, you can see the drainage coefficient. So two effects, subbase and subgrade strength or stiffness, joint load transfer effectiveness. So due to saturation, you can say we are having these two effects, and we have already seen this type of table in the case of flexible pavement, but here you can see we are using the symbol C sub D, and in flexible pavement we use the symbol M sub I. So here again you can see the percent of time pavement structure is exposed to moisture level approaching saturation, and this is the worst case which has been considered over here, and the quality of drainage you can see over here. So by using this table we can determine the drainage coefficient C sub D. But keep this thing in the mind that this table is different table from the table that we considered in the case of flexible pavement. Values are less in the case of rigid pavement. Well, PCC, modulus of elasticity, E sub C, measured directly per ASTM C469. Correlation with compressive strength is available, like you can see this one, that elastic modulus in PSI is equal to 57,000 into the square root of Fc prime, where Fc prime is the compressive strength in PSI per AASHTO T22 T140 or ASTM C39. Effective subgrade modulus K, it depends upon the roadbed subgrade resilient modulus M sub R and subbase resilient modulus ESP. Both vary by season, you know. Subbase resilient modulus ESP, or you can say the modulus of elasticity of subbase. Well, on this particular slide, some useful information is given regarding the determination of the effective modulus of subgrade reaction. So you would find the table 3.2 on the next slide. So different important things: identify subbase types, subbase thicknesses, loss of support, LS, that is erosion potential of subbase, depth to rigid foundation. Depth to rigid foundation means from the top of the subgrade. If you are having a rigid material, a rock or some rigid strata at a certain depth, so the vertical distance from the top of the subgrade to that rigid foundation or the rigid formation, that is called as the depth to rigid foundation. That is measured in feet. Assign roadbed soil resilient modulus M sub R for each season. Assign subbase resilient modulus ESB for each season. 15,000 psi spring thaw, and ESP is greater than this one and it is less than 50,000 psi, which is in the winter when the water has been frozen. And one more thing, that ESP is less than 4 times of M sub R. Now this is the table 3.2, and you can see here type, thickness in inches, loss of support LS, depth to rigid foundation in feet, and the projected slab thickness in inches. If you just look at this table, there are 6 columns. The first column is for the month. The second column is for road bed modulus, that is M sub R in PSI. Column 3 is for subbase modulus ESB, again in PSI. And then you can see the composite K value, modulus of subgrade reaction in pound per cubic inch, and we will get it from figure 3.3. And column number 5, you can see here K value in PCI on rigid foundation from figure 3.4. And then come this column, and here you can see relative damage U sub R, and it will be determined with the help of figure 3.5. And here at the bottom you can see the average U sub R, that is the summation of the U sub R divided by the total number of months. Then effective modulus of subgrade reaction in PCI, and then corrected for loss of support, that is again in PCI. So determining effective K, continuing that, determine composite K for each season. For TSP is equal to 4. That means when the thickness of the subbase is 0, then K can be determined by using this formula, MR over 19.4. But when we are going to provide the subbase, that means DSP, the thickness of subbase is greater than 0, then figure 3.3 is to be used. If depth to rigid foundation is less than 10 feet, correct K for effect of rigid foundation near the surface. It means if the depth to rigid foundation is more than 10 feet, then you don't need to apply this correction. But if depth to rigid foundation is less than 10 feet, then correction is to be applied with the help of figure 3.4. Estimate required thickness of slab using figure 3.5 and determine relative damage U sub R for each season. Use average U sub R to determine effective K with the help of figure 3.5 again. Then correct K for potential loss of support LS. Figure 3.6 will be used in this regard. Well, here you can see the figure 3.3, and here you can see that K, the composite modulus of subgrade reaction, is the function of M sub R, ESB and DSB. So you will have to use these values, so you will be able to get the composite modulus of subgrade reaction. So here look at this one. This is the subbase thickness. These curves are meant for subbase elastic modulus. These curves, these lines are meant for composite modulus of subgrade reaction. And these curves I have already mentioned. This is the road bed soil resilient modulus. So I will repeat these curves: road bed soil resilient modulus. These curves, sub-base elastic modulus, and these curves or lines are meant for composite modulus of subgrade reaction, and this scale is meant for the sub-base thickness. So let's say the sub-base thickness is this one. So move vertically in this way and go up to that particular curve which is matching with the sub-base elastic modulus. Now from this point you will have to move horizontally, but before that, from this point, which is corresponding to the sub-base thickness, move downwards up to that value, the value that you are having for road bed soil resilient modulus. Then move horizontally like this. This is the turning line. From this turning line we will move vertically in this way. From this point we will move horizontally. So the point of intersection will give you the value of the composite modulus of subgrade reaction. So in this way we can get the composite modulus of subgrade reaction by using this figure, which is the figure 3.3. Well, if you just look at this example, here the thickness of the subbase is 6 inches, ESP is 20,000 psi, and the modulus of resilience, that is 7,000 psi. So after carrying out this exercise, here we have got the composite modulus of subgrade reaction, that is 400 psi. Well, if you just look at this particular figure, this is figure 3.4. Rigid foundation correction is to be applied in case because when there is a rigid foundation is present closer to the top of the subgrade, then it means there will be increase in the K value due to presence of the rigid foundation. So if you just look at this particular figure, this scale is meant for roadbed soil resilient modulus, and you can see here different curves, and these curves are meant for the depth, subgrade depth to rigid foundation, DSG, and these curves are meant for modulus of subgrade reaction, okay, and this axis, this is meant for the modulus of subgrade reaction K in PCI, and if you just look at these values, I mean to say the lines, the values are written. So if you just look at this particular example, so the things would be clear. In this example, the modulus of resilience is 4,000 psi, DSG, that is the subgrade depth to rigid foundation, that is 5 feet, and the modulus of subgrade reaction, which is given, that is 230 psi. We want to correct it. So how can we do it? Look at that. First, look at the roadbed soil resilient modulus, that is 4,000. So you are here. Then move upward up to this curve, which is meant for 5 feet. The subgrade depth to rigid foundation 5 feet. Then move horizontally and just look at the modulus of subgrade reaction, which is given in the question, that is 230. So 230 line is somewhere here. So you can move up to this particular point and then move in the downward direction. So this will give you the corrected modulus of subgrade reaction, and that is 300 psi. So in this way we have got the corrected modulus of subgrade reaction after applying the rigid foundation correction. Now look at this one. This is figure 3.5. Relative damage is function of K and the depth of the concrete slab. Well, either we can use this figure, which is figure 3.5, to get the relative damage, or we can use this formula to determine the relative damage. So here D is the thickness of the concrete slab, K is the modulus of subgrade reaction that is to be corrected. So either by using this equation or this formula or by using this chart we can get the relative damage. And there is one important note is written: the minimum allowable thickness of PCC pavement shall be 230 mm 9 inches for interstate routes and 200 mm, that is 8 inches, for all other roadways. So simply you can say that for interstate routes 9 inches is the minimum thickness of the concrete slab. So you can see, let's say in this particular case, if let's say the modulus of the subgrade reaction is this one and the minimum thickness of the concrete slab that we are considering, that is 9, so you can see that the relative damage value is coming this much. So this is in percentage, but it will be considered as fraction. So simply by using the modulus of subgrade reaction value going up to the curve which is showing the thickness of the concrete slab, as I have mentioned that the minimum thickness of the concrete slab is 9 inches, so we have considered the 9 inches over here. So in this way we have got the relative damage. So in this way the relative damage can be determined very easily by using this particular figure, which is figure 3.5. Now in this particular slide you can see the example, and you can see here 12 months are mentioned, and then look at the column 2, 3, 4, 5 and 6. We have already discussed these columns. If you just recall those columns that I have already discussed with you, the column 2 is the roadbed modulus m sub r in psi. Column 3, that is the subbase modulus ESB. Column 4, that is the composite K value in PCI by using figure 3.3. This is the column 5, K value in PCI on rigid foundation by using figure 3.4, and this is the relative damage U sub r using figure 3.5. So here we are having the values of the roadbed modulus m sub r for different months, and then on the next column, subbase modulus ESB are known to us, and we have written these values over here, and then the composite K value has been obtained by using figure 3.3. then the K value on rigid foundation by using figure 3.4, and then the relative damage by using figure 3.5. So we have got these values, then just by add all these values, this is the sum. This sum will be divided by 12 to get the average relative damage value. And then you can see the next thing which is mentioned over here, that is the effective modulus of subgrade reaction PCI, and then corrected for loss of support. Well, this I will explain, but on this particular slide I think the things are cleared up to this. This is the effective modulus of subgrade reaction. So by using this value of the average relative damage, we will use the figure 3.5 again, and by using the figure 3.5 we would be able to get the effective modulus of subgrade reaction in PCI, and this is this much in this case. Okay, the next thing is the corrected for loss of support. To understand that, we will have to switch over to the next slide. Well, on this particular slide you can see that the type of the material are mentioned and the loss of the support LS ranges are mentioned. When we are using unbound granular material, so E value is from 15,000 to 45,000 psi and the loss of support is from 1 to 3. Likewise, for the other cases we are having these different ranges. There is one important thing which is mentioned over here, that the subbase or subgrade erosion at joints causes loss of support, impairs load transfer. Impairs means weakens load transfer. Well, if you just look at this particular slide, you can see here this axis is meant for the effective modulus of subgrade reaction K in PCI, and this one is meant for effective modulus of subgrade reaction corrected for loss of support. Let's say LS value is 1, so what to do? The K value that you are having, the most corrected value so far, you are having this one. So using this and considering that, you can say this is 170. So with the help of that figure 3.6, we can determine the corrected effective modulus of subgrade reaction for potential loss of subbase support. And if you just look at this particular slide, here you can see that ultimately we have got the corrected value, the most corrected value of the modulus of subgrade reaction after considering the loss of support, and this is 170, that is 170 PCI. So at the end I would like to say this thing, that the modulus of subgrade reaction is very, very important in the rigid pavement design method. So different corrections are to be applied on the modulus of subgrade reaction value, and after applying all these necessary corrections we will be getting the effective, or you can say the most corrected value of the modulus of subgrade reaction, and that value is to be used in the nomograph. And you know, the use of nomograph, ultimately we will be getting the thickness of the concrete slab, that is the thickness of the rigid pavement. Thank you.